So the next speaker will be Staton. Just setting up. And he's going to speak about the equational characterization of quantum computation. Please go ahead.
Right. So this is a talk about some work I've been doing which I think serves two purposes. One is to give a convenient way of using equations to manipulate quantum programs and understand them. And the other motivation is to understand the usual model of quantum computation using positive uniform maps, but to derive it from a simple equational theory. So let me say a bit about what I mean by quantum computation. First of all, we might draw quantum computations like this as circuits, as you'll see, for example, in the book by Nielsen. Let me read this one to you because I'll use it again. Okay? So in comes a qubit A, and then we generate a new qubit initialized at 0, rotate it by the Hadamard unitary, and then measure it. Depending on the measurement, we flip the phase of A. Well, what does it mean to measure in the Hadamard basis? It means to measure 0 in the Hadamard basis. It means to randomly generate true or false. So in other words, this circuit randomly flips the Z phase of A. You could also describe that program, that computation, by programming a programming language, and there have been lots and lots of work on good programming languages for quantum computation, for defining structures like that. Here's a little example of what that might look like. So what I want to do is talk about what equations hold between computations like these. And in order to do that, I want something really simple. In this circuit, we're having to talk about classical wires. Now, we've known for over 100 years what the properties of classical circuits are. So I don't want to axiomatize that. Similarly, in this programming language, we've got a Boolean here that we're then doing an if, then, else. And we've known for quite a long time what the properties of Booleans and if, then, else are. So I don't want to axiomatize that. I just want to axiomatize the notion of quantum computation. So let me just cut to a sort of more canonical kind of description. One could replace this classical wire by a branch in the circuit. I don't know if I've never seen this picture in print before, but it seems a very sensible way of illustrating the point that when you make the measurement, you decide between either continuing as flipping the phase of A or as doing nothing. You see this kind of branching thing of 2D space in illustrations of many worlds quantum physics. But also you see them in Paul-André Mellier's work on store for classical data, nothing to do with quantum physics at all. Now, I don't want to really be drawing 3D diagrams like this, and sometimes it becomes unclear what they mean. So for now, I'll stick with a syntactic formalism which describes exactly the same thing. And let me read this to you. So we've got this qubit A coming in, and then what we do is generate a new qubit B, initialized to 0. I'll be more formal about what this syntax means a bit later. We then apply the Hadamard gate to B, giving us a new qubit B prime. We measure B prime, and depending on the measurements, we either return our continuation is past A, or we apply the Z gate and pass the result of that to our continuation. So you see this inside this expression, there is no if, then, else, there's no Booleans. It's just the quantum constructions of new qubits, gates, unitary gates, and measurements. That's the formalism I'm going to work. Before I do that, let me just say a little bit more about the relationship between algebra and programming languages, because that's my background. That's what I've been looking into for the last 5 years or so. So a generalized kind of algebra is the world of so-called enriched Levere theories. These are presentation pre-descriptions of algebraic theories in a slightly general sense. And the original notion was due to perhaps Max Kelly and John Howard, but I've been working on it as well. On the other hand, what's an equational theory of a programming language? Well, at least a first-order programming language, no higher types and no recursion, can be described as what's called a Frey type. An equation theory of a first-order programming language. And actually, they're the same thing. They're just dual tools. In fact, this correspondence between programming languages and algebra is really, really precise. Actually, some of you may have seen notions of computation described by monads, and indeed, finitely strong monads are the same as both of these other two things. You can move between the three things. Well, let me come back to quantum computation. What I want to say is that this really fits in just a general framework of notions of computation. So what is the algebra for quantum computation? Well, here was something where we performed a measurement, and then depending on the outcome of the measurement, we flipped the phase of A. Well, this conditional gate can be pushed across the measurement so that we do a conditional unitary, flipping A in a quantum way, depending on what B is. So that's an example of an equation of quantum computation. It's going to be one of my equations later. So a summary of my main theorem is that the following are equivalent. First of all, a computation expression modulo the equations that I'm going to show you. And secondly, a completely positive unital map between Z-star algebras. I'll be more precise about that later, but I want to understand what the main result is. So let me go into some detail. First of all, the terms of this algebraic theory, the ways that we can define quantum computations in this formula. Well, let me be informal to start with. If A is a qubit and T and U are computations, then we can build a new quantum computation that first of all measures A in the standard basis, and then depending on the outcome continues as either T or as U. Slightly more formally, we could say if we've got a computation T and a computation U, then we have a computation measure A, T, U. Measures A, continues as either T or U depending on the outcome. To be even more precise, I think it's always good in algebra to write down what your variables are. So let me put some variable context. There's going to be two kinds of variable, one kind ranging over the qubits, and one kind ranging over the computations. So the red context, the gamma, is the computation variables, and the delta is the qubit. So what you see is that once I measure A, I continue as either T or U, but actually the A can no longer appear in T or U. That's because it's been measured, it's been collapsed, it's no longer a piece of quantum data. So in general, I'm going to look at judgments like this. This is a judgment with three parts. The first part tells you what the computation variables are. I'll talk about the M's in a minute. The second part talks about the qubits. And the third part tells you what is the computation expression. Now the computation variables are annotated with numbers, that's to say how many parameters they may take. If you think of them as being the continuation of the computation, then maybe the continuation depends on some qubits that have been formed during the computation. And then the term formation rules for quantum computation consist of three things. First of all, measurement. Secondly, new. What this is saying is if you've got a quantum computation involving qubit A, you form a new quantum computation that allocates A, initialized with 0, and continues as T. Lastly, if we've got a quantum computation T, it depends on, in particular, n qubits. What we can do is build a new one, which first applies a unitary gate to the n qubits, here called A1 to AN, produces some new qubits, B1 to BN, and continues as T. Let me just emphasize some of the syntax. So A dot T means A is binding in T. That's like exist A T in predicate logic, or lambda A dot T in lambda calculus. Its variable binding is up to renaming of variables. Similarly, down here, B dot T binding of these. And also, I can emphasize that these qubits must be treated linear. We're used to the idea that qubits can't be duplicated. They can be discarded, but I won't put that implicitly in the system, but we'll see that discarding can be defined. So that's all the important instructions of quantum computation, at least in this sort of sense. And then finally, the law for variables says a variable x can be given p qubits in the environment. I'll have the exchange law as well, so you can reorder it. Now some examples of things you could write. So if I've got one continuation variable, one computation variable, I can form this program, which first allocates a new qubit, then flips it around the z-axis, and then returns, and then calls continuation x with the result of that. So what that's going to do is allocate something at 0, flip it around and return it allocated at 1. And to just show how these typing rules work, if you've not seen type theory before, we can derive the well-formedness of this term from the axioms. So first of all, this is a new at the outside, so we put the A into the context, then we check that apply x, A, B, x, B is okay. Well, we do that by checking that x, B is okay, and that's the variable. Here's another example. This is something that creates a new qubit, measures it in the other basis, and either continues as x or as y. Here, x and y don't take any parameters. What this is going to do is randomly continue as either x or as y. And then putting that together with and apply z, we can describe the computation that we saw at the beginning, which randomly flips the phase of A. So these computation variables, you can think of them as standing for continuations, but in the algebra they form just as in normal algebra, you can substitute other expressions for the variables, and we still have a well-formed. That's the key role that variables play, is that you can substitute other expressions for them. Just to emphasize that even this algebraic framework doesn't quite look like normal algebra because of this variable binding and because of the two contexts, but it's extremely useful in other areas of maths and computer science. For example, you can formalize first-order logic. Here is the introduction rule for existential formation. If I've got a term involving a variable A, I can build exists A. Disjunction, a similar kind of pattern to measure. And I've used the same framework to axiomatize also pi calculus, lambda calculus, local score, and various things. It's a very flexible way of describing different notions of computation, in particular quantum. Okay. Let me talk about my axiomatization of equality. Before I do that, let me say that because I've assumed just we can apply any unitary gate, I don't have an axiomatization of the unitaries. Oh, I haven't talked about that. That's not the main idea of this piece of work, but rather to assume that we've got the groupoid of unitaries. Many people, of course, are working on very nice axiomatizations of the unitaries and ways of approximating them, and that's not something I wanted to look at just now, but rather to assume we've got the unitaries and then to understand how unitaries interact with measurement and new generating qubits in order to build from the unitaries the theory of completely positive unitaries. So a groupoid is a category in which every map is an isomorphism. The groupoid of unitaries, I say, has objects, natural numbers, and morphisms, unitary complex matrices. And this groupoid has two symmetric monoidal structures. The first one, well, on natural numbers, we take the product of natural numbers. On maps, we take the Kronecker product of unitaries. And it's a symmetric structure, and the symmetry is generated by the swap gate, the gate that swaps two whites. So what I need to do in my equations for quantum computation is to reflect this structure inside my algebraic framework. So here is the algebra, and here are some illustrations to show you what's going on. So if I apply the unitary V, and then I apply the unitary V, it's the same as applying the unitary UV. If I apply the unitary U tensor V, it's the same as doing U and then V. And if I apply the swap unitary, it's equivalent to using the exchange law, which I have in my syntax, to swap the variables. The multiplication structure of the groupoid of unitaries must be respected. That's what these kinds of equations say. The second symmetric monoidal structure that unitaries have is the sum. You can take two numbers and add them together. And when you do that, you take two unitary matrices and you form the block diagonal. That's going to be a unitary between the sum of their remains. And that's again a symmetric monoidal structure. The symmetry is generated by the not get. These diagonal matrices in particular contain a way of describing the conditional. So now I want to say that in the syntax, that measurement interacts with the sum structure of the groupoid of units. So let me say that. Here again is the algebraic expression for saying that, but you can draw it in diagrams in this case. It says if I measure, and then depending on what I measured, I apply the unitary u or the unitary v, it's the same as applying a controlled unitary, u or v, and then measuring afterwards. And so the controlled unitary is just the block diagonal of u. Secondly, to say that the symmetry of the groupoid of unitaries is respected, I say if I apply the not gate and then I measure, it's the same as measuring and then applying the not gate. Well, I don't have classical wires here, but I can still say that if I measure a x, y, it's the same as measuring a and then continuing as y or continuing as x. I flip the continuations around. So these two axioms I think of as the interesting ones. The other three are just a little bit kind of bookkeeping. These are two of the interesting axioms. There's one third interesting axiom. First of all, let me define discard. What does it mean to discard a list of qubits? Well, it just means to measure them all and then forget the results. So if I discard no qubits, this doesn't do anything. If I discard A and then I discard all of B, it's the same as measuring A, and then regardless of the result, I forget the result and I discard the rest. It's an inductive definition of discard. And now my axiom, what is really an axiom scheme, says if I apply a unitary and then I discard all the things involved in that unitary, I needn't bother applying the unitary. This is my third interesting axiom. And in particular, by the way, when n is 0, this says that global phase doesn't matter, because a 2 to the 0, 1 by 1 unitary, is just a phase rotation. So these three axioms I think of as the three key axioms. I think they're intuitive, I think they make sense. Thirdly, let me come to talk about the completeness theorem. Have I got all of the axioms of quantum computation? I mean, I should say, there are, I think, three other bookkeeping axioms about how things commute with each other, and then a couple of axioms about mu as well, but I haven't shown you, but they're in the paper. There's 12 axioms in total. Well, what I'll do to show that I've got all of them is to, rather than just appeal to the fact that I've tried to find others and couldn't, which is something I've also done, I'll show that any term can be interpreted as a linear map, and if any two terms induce the same linear map, then their equality is derivable. So I won't describe exactly the way to interpret a term as a linear map here, but let me just explain what's going on. So when you see a map between C-star algebras, I think computationally you look at it as going the other direction. So this says, given p qubits, I will either return m1 qubits or blah blah blah, I will return mk qubits, depending on what measurements are made and what new quantum information is made. And then the theorem says that every such completely positive unital map is the interpretation of a term. That's something that I think was well known, that any completely positive map can be described by creating new qubits, applying some unitaries, and then doing some measurement. Indeed, it was made quite precise in Peter Salinger's work about 10 years ago. But on the other hand, couldn't find this result anywhere. Two terms are interpreted as the same linear map, if and only if their equality is derivable from my equations. That's those three equations about how measurement interacts with, two equations about how measurement interacts with the sum structure of unitaries, the product structure of unitaries is respected, and then this special axiom about discarding. And I proved that result by using a kind of variation on Stone-Springs theorem, and also Bertelli's characterization of star homomorphisms between finite-dimensional C-star algebra. Probably the hardest part about the proof was the Stone-Springs dilation theorem tells you that you get finite, you can factor a completely positive unital map into a star homomorphism and then an isometry on the Hilbert space. But it doesn't tell you, it tells you, well, in the books they say that the factorization will be finite dimensional if you start with a finite dimensional thing, but it doesn't say that the factorization will be into a power of 2. Indeed, it probably won't necessarily be into a power of 2. So my worry was that in order to prove equality between quantum terms, you would need to introduce a type of Q trits and Q quits and so on. And so the difficult part of the proof was really to show that one doesn't need these different number bases, qubits, in order to reason about equality between terms only involving qubits. So, in summary, I've given you an equational theory of quantum computations, and it fits within this general basic framework which supports, as I said, many other notions of computation besides quantum. And it gives you a complete axiomatization of completely positive unital maps between C-star algebras, hopefully giving an intuition and a tool for reasoning about quantum programs, but also giving a formal motivation for theory of completely positive unital maps, rather than jumping from some informal intuitions directly to the linear algebra. We can step through this formalism of algebra. Thank you.
Thank you, Sam. Are there any questions?
In the previous slide, you mentioned the proof of this main theorem.
Yeah.
And you told that you used the Staton theorem and the Bertelli's characterization of star homomorphism. What is this characterization?
Yeah,
Yeah.
it's quite popular in the theory of approximately finite-dimensional C-star algebras. So it tells you how many, if you've got two finite-dimensional C-star algebras, you want to know how many star homomorphisms are there between them. And Bertelli's characterization gives you the number modulo unit.
Bertelli diagram.
Yeah, Bertelli diagram. Yeah.
What's the proof idea of the second part? You reduce all the terms to some kind of normal form?
Yeah. It's not quite a normal form because of some things can be affected. That's not. And Stone-Springs theorem is also a kind of a normal form theorem.
Any other questions?
How about recursion?
Yeah, okay, so that's a very good point. So I said at the beginning about this relationship between algebraic theories and first-order programming languages. Well, because, as I said, all of this is taking place within quite a general framework, people have thought about recursion and higher types and so on for programming languages and how to add them to a first-order theory of programming. So one can follow that, hopefully, and see where it leads. I should also say that if we take sub-unital maps, and this is in the paper, then Peter Selinger also already explained how you can get iteration for automatic.
Okay, any more questions? No? Well, thank you again, Sam.